Hello and welcome to our webinar, Selecting, Defining and Specifying Aluminum Foundry Alloys. My name is Martin Hartlieb and you can find my contact details at the end of this presentation, so if you have any questions, feel free to contact me. Before we get started, I would like to point out that we have two other webinars that I would recommend that you also watch, and one would be the Introduction to Aluminum Foundry Alloys and Metallurgy, because there we explain all about the different foundry alloy families, alloying elements, impurities, and achievable properties and applications. And the other one would be casting technologies, where we explain the different casting processes and how they work and what are their advantages and disadvantages. So just to quickly recap from that one, in terms of foundry process selection, if you usually start by selecting the right process, or you already have only one or two processes, then it's not even a question. You want to first look at the volume and economics, so investment in equipment and in molds versus the part price. If you have a very large volume and certain requirements like good surface finish, tight tolerances, things like that, well, then die casting might be the right option. Just be prepared to have pretty high investments in dies, for example. If your volume is low and maybe your surface finish requirements aren't that strict, then maybe sand casting is the right choice, because part price might be higher, but you don't have much of an investment in dies or molds. Then things like wall thickness requirements, as I mentioned, die casting can give you very thin walls. Sand casting would be rather suitable for thicker walls. If you need small volumes but you need thinner walls and good surface finish, well, then there are compromises in between. Sometimes you can even get low pressure sand casting or investment casting, things like that. So there's always a way to find a good compromise for what you need. Same thing with tolerance requirements. Again, depending on the process, they can be better or worse. Surface quality requirements, as I said. And then, of course, mechanical properties, fatigue, strength, and so on. They all depend primarily on the freezing rate of the aluminum alloy, and therefore on the process, because, for example, in die casting, you have a very high freezing rate. The metal comes into contact with a cooled steel mold, so it freezes very quickly, especially if it's thin-walled, versus in a plaster cast, the molds are made of plaster, or sand cast, molds are made of sand, and then it contracts even away, so you have an air barrier between the mold and the solidifying casting. So you can imagine the solidification is much slower, and therefore the microstructure will be more coarse, and this will affect the mechanical properties. Once you've determined what is the right process for you, that will actually now also determine which alloys you can choose or which ones are really not suitable for the specific process that you have chosen. So you might have to revisit your process choice after you know, okay, well, I have those requirements that require this type of alloy, so maybe now I have to adjust a little bit on the process side. So you have to look at those two things together and make the best choice of a compromise between the alloys and the process. The casting process you are choosing will, first of all, determine your casting properties. As we said before, it determines the mechanical properties, but also tolerances, the surface finish, and so on. It also determines casting quality, how much porosity you will get. Slower freezing processes will tend to give you more porosity than faster freezing processes. Same with microstructure. Faster freezing gives me a more fine microstructure, and so on. Then process costs and initial investment that is required. If I have to go into sophisticated steel molds, or if I can do just a wooden pattern and then create sand molds around it. And of course, metal costs, very important. It will determine the alloy types and limitations that I can use for this process, the required purity that I will need, and the ability, therefore, to recycle scrap internally or use recycling content in the alloy that I'm getting, and the ability to use different ingot forms or even liquid metal supply. With this in mind, we will cover in this session, first of all, casting properties, selecting the right foundry alloy as an OEM or a casting buyer. Then we'll talk about what not to do, because this is very important. And then we talk about writing an alloy casting and purchasing specifications. So what should you be doing? Then we talk about defining testing and quality assurance for alloy and castings, and the cost drivers in aluminum foundry alloys. So casting properties. Castings rarely have just one single set of properties. The properties will depend on the microstructure, and therefore it can be very local. So in a thick section, the properties will be very different to a thin section because the microstructure is different. It took longer or shorter time to solidify in this area. So local solidification rate interacting with gas and dirt, if we have more impurities in a certain area, this will all affect microstructures and therefore casting properties. Now, mechanical properties will have a certain average and a certain spread, and very often the design properties must take both into account. Very often you will see that somebody will design to, let's say, the average minus 3 sigma, for example, to have a safety margin in there. Castings frequently even have a time-based component, so there's a slow, gradual chemistry change. There can be even seasonal changes. And now the first economic law of casting, if you have not heard that from me before, so absolute perfection 100% of the time costs an infinite amount of money. So if we have a look at comparative mechanical properties in different foundry alloys, and I always like starting with the standard foundry alloys, and that I would say is the A356, usually used in castings in the T6 temper, so solution heat treated and peak aged. And to remember it, I use 30, 40 and 5 to 10% elongation if you think of KSI. So in megapascal, the mechanical properties would be 205 approximately yield strength, 275 tensile, and 5 to 10% elongation. Now, if we add more magnesium, we get to the 357 alloy. That's mostly used in aerospace applications. So the higher magnesium content will give us more strength. So instead of 30, 40, I'm actually at 40 and 50, but it comes at a cost, and that is in our case now elongation. So instead of 5 to 10%, I will usually be between 3 and 7%. We can also see here, if we want to have a quick look at it, higher temperature, because we have mag silicide hardening, we will see the properties drop very quickly. Just at 150 degrees Celsius, we can see already the alloy gets very, very soft. So our 30 and 40 just drops to 17 and 29, but the elongation goes from 5 to 10 up to 15 to 20%. So very quickly we gain elongation and we lose strength, because especially as of 150 degrees Celsius, the mag silicide hardening doesn't really work anymore. Now let's have a look at something completely different, the 535 alloy, also AlMag 35, and that is an F temper, because this is a binary aluminum magnesium alloy and no heat treatment required, doesn't really do anything. And we look at the properties, that would be 140 megapascal or 20 KSI yield strength, 40 KSI or 275, just like the A356 in T6 in terms of ultimate tensile strength. But what's very impressive, S-cast a 13% elongation here, so this is a great set of properties, but it is a lot more difficult to cast, of course. So everything comes at a certain cost, of course. Let's have a look at something completely different, a very strong alloy, the A206 in two tempers, the T4, which is the softer temper with a higher elongation. So I can achieve up to, let's say, 17% elongation we got here, but I can see in T4 I got 38 and 62 KSI yield and tensile strength. If I want it even stronger, then I give it a T7, so it's long-term stabilized, and now I'm at 50 KSI yield strength, 63 tensile, but my elongation has dropped to just 11 to 12%. Now this is with aluminum copper, and copper is temperature stable until we usually say about 250 degrees Celsius. So we can see here that still at 175 degrees Celsius, our strength is still much higher with the T7 tempered casting, and we gain some elongation, but it's not that bad. So 44 KSI and 17.7% elongation here. If we want even more temperature stability, then what we can do is the 242 alloy is also aluminum copper, but now even nickel is added. And in this case, we can see here at room temperature, we have 34 and 40 and just 1% elongation. So really no elongation. This is used where you don't need ductile castings, but the beauty is at 150 degrees Celsius, I pretty much have exactly the same properties as at room temperature. If we talk about selecting the right foundry alloy, let's first have a look at the view of a casting buyer. My first recommendation for you is define what you really want. Define what you really need in the casting. And usually I would say this is, for example, mechanical properties, and you want to define them where you need them, for example, at room temperature or at elevated temperature. Define all the things that you really need the casting to be able to perform. Any kind of other properties like conductivity, electrical or thermal conductivity, corrosion resistance, and define how you want it to be tested. Maybe even recycling content or a carbon footprint. This is something that's becoming more and more important. And then choose the right alloy family first, and then the right alloy type if you have to. It needs to be compatible with the chosen casting process, of course. If not, then you have a problem. Then you have to go back and adjust and either choose a different casting process or adjust the alloy or use a different alloy. Then, of course, is it compatible with a given part design? Because depending on the alloy, you might get all the properties that you need, but it will be nearly impossible to cast, let's say, a very complex, intricate design. And is it compatible with casting exposure, whether it's exposure to heat, corrosive environment? For example, aluminum copper alloys typically are not as corrosion resistant as especially the aluminum magnesium alloys, things like that. And is it compatible with the assembly, all your subsequent process steps? And let's say you want to have it anodized afterwards. Well, that limits your alloy choices. Then you might have to go to a 500 or 700 series alloy. Finally, of course, is it compatible with your supply base? Because you might not want to end up with just one possible supplier in the world. So availability and price. So now I would recommend you define casting specifications with quality gates and especially testing procedures in place to ensure the casting and alloy quality. So rather than specifying a certain brand name that you've heard has high quality, rather really define how you want the quality to be measured and to be tested. So which testing should be done how often? For example, chemistry with a spectrometer, well, you want it to be done every time you melt it. And if the furnace was sitting overnight or over the weekend and you start back up Monday morning, you want to have it tested again. You might want to have this tested both at the casting plant and possibly at the metal supplier and even downstream process steps. So all the testing that you want to have done and when, how often, specify that. Where in the casting should the tensile bars be taken? So you specified your mechanical properties, and I said before, the mechanical properties will never be the same everywhere in the casting. So you really need to define, okay, here, these are the areas that are very important. Those might be the areas that are exposed to something. This is where it's mounted. This is where it's going to be riveted. So this is where I really need my 10% elongation. And here I have an area that is just there and there will be not much tension on it or not much pressure on it. So there I can live with lower properties. Define which defects are acceptable. I said it before, the perfect casting will cost you an infinite amount of money. You have to live with a certain porosity. I find it funny when I see a casting drawing or specification that specifies the casting has to be porosity free. It just doesn't work. But define what porosity is acceptable. If it's heat treated, solution heat treated, also you might want to give a blister specification. Maybe some very small blisters are acceptable for you. Maybe it's even acceptable that you treat blisters or porosity in a certain way. And last but not least, define the homologation process for the supplier, for the casting supplier, and for a specific casting, possibly including the metal supplier. You might want to homologate a certain metal metal source where you know that everything is under control, everything is high quality, just as I am expecting it to be in my casting. So now, what do you want to do if you have to select the right foundry alloy as the foundry, as the die caster? So you receive a specification from your OEM, your customer, the casting buyer, hopefully a specification that doesn't just call out one brand name alloy that you can buy from one source in the world, and then on top it says that your casting needs to be porosity free, because then you certainly have a problem. And here again, same recommendation: define what you and your customer really want and really need. That's what you want to tell or communicate to your metal supplier. So obviously you look at what is on the drawing, what is in the specification, and does it need clarification? An alloy or heat treatment can have many different property packages, so you need to define targets and you need to find minimums, etc. Don't just assume it. Don't just assume your metal supplier will know what you want to do. Even with impurities, I have seen specifications for die castings, for example, and they have just a maximum for iron. So you get a very good alloy from your alloy supplier and it comes with a very low iron content, and then all of a sudden you're struggling with die sticking because you actually needed a minimum of iron to beat die soldering. So even if you think, it's kind of self-evident, make sure you define what you really want. Define your targets, minimums, maximums, etc. Also define how you can test it, and everybody will accept the tests and the results. Otherwise, you will have just battles with your customers later on. Then again, first define the alloy family and then the alloy type, and then work on the exact chemistry. Make sure you take all part requirements into account, the process itself and the process limitations, what you need. For example, if it's die casting, you might need a minimum even on iron, or you need to have certain element combinations defined. So your iron and manganese together should be between 0.7 and 0.8, for example. So if this is important for you, then specify it. Don't just assume that your metal supplier guesses or knows it. And calculate any losses during the melting, melt treatment and transfer and casting, and define what you want to add yourself and what should be already in the ingot. We'll get to that. And we saw that in the other webinars if you looked at that. So calculate the chemistry with the internal scrap returns and what you lost and picked up. For example, iron in any kind of steel molds, you will be picking up. Magnesium and strontium you will burn off. So all these things, you need to take them into account, and with all of that in mind, you want to create your purchasing specification for the metal supplier. So with that now, I would like to point out a few things I do not want you to do. Let's start with copying an existing specification or parts of it from a completely different part. Just because you say, it's kind of similar to this one, I just copy it without even looking through it. So very often in this case, you will find things on the drawing in the metal spec that just made the ingot a lot more expensive for no reason at all. The next thing is, I mentioned that before, just choose a brand name alloy. Unless you own the brand, of course. So if you are Mercury, then you might just want to specify a Merc alloy because, that's what you make yourself and you use, of course. But if you're not the owner of, let's say, the Silafon 36 alloy, then you might not want to put just the brand name on it, because even if you specify Silafon 36 T7, if we look at the properties here, they can be anywhere between yield strength 120 and 170, tensile 200 and 240, and elongation 15 to 20%. What exactly did you want? If we look at the chemistry, the chemistry is defined at 0.1 to 0.5% magnesium. Very simple. If I'm at a lower magnesium, then I will have less strength and I will be at the high end of elongation, the other way around. And please don't come and tell me now you want the maximums everywhere, so you want 170, 240 and 20%, because that unfortunately will not work. So all these things, you really want to specify what you want as the OEM or casting buyer. You, as I said before, specify your properties that you expect, and then as the casting producer, then rather specify the chemistry and narrow down, in this case, for example, the magnesium content that will give you the properties that the casting buyer is expecting from you. So otherwise, you will just risk that you might have only one single source at a very high price. The next mistake that I often see is, well, because you know it, you say, oh, I just specify a standard alloy, like A356T6, without further definition of the exact properties that you want. It's just, oh yeah, I'm familiar with it. And you might want to do that because you say, well, this gives me the largest selection of suppliers because it's the most standard alloy. Yes, but maybe you rather want to define what you actually need in terms of properties, because maybe somebody else is able to give you those same properties with a slightly different alloy, maybe a slightly different process, and you might even get it cheaper than you thought. Then specify things that might or might not improve casting quality. I love these phrases on a drawing or specification. Only use primary metal, so no recycling content. It is possible to have recycling content without compromising the mechanical properties or any properties of the casting. And you can have all primary metal and still screw it up in the process and then have bad properties or bad quality. So just the fact that you specify something that you think improves the quality does not improve the quality. Same thing if you say only use ingots and no internal returns or scrap. Again, if somebody knows well how to deal with it and how to treat scrap and internal returns, then that can really reduce your price and does not necessarily have any negative impact on your casting property. And do not dictate the exact casting process and parameters unless it is really important for you and you are sure no other process could fulfill your requirements. If you leave a little more freedom to your casting supplier and you let them actually figure everything out, you also know that if something goes wrong, they actually know why they are doing it, why they have chosen those parameters, and what small variations will do to the casting and the properties. So they can actually fix problems much better than if you just go and tell them exactly what you want them to put into the machine. So now let's look at the different alloy types, alloy families. And if you watch the other introduction to Foundry alloy webinar, then this will partially be repetition for you, but we'll go through it very quickly. So 300 series alloys, we have to start with that because it's the workhorse of our foundry industry. They have very favorable characteristics, unique to aluminum silicon alloys. They are largely immune to hot tearing, a big problem with other alloys like 200 series high strength alloys. They are very castable in terms of fluidity, feeding. They are relatively inexpensive because they are commodities, especially, of course, die casting the 380 alloy, A380, and in terms of the primary alloys, the A356, for example. The 300 alloys should be considered when the part in question is very complex. It's not possible to achieve steep temperature gradients, so directional solidification is not possible, and it is impossible to avoid mechanical restraint, therefore, during the solidification. You would also choose them if there is just no reason to specify one of the other alloy families, because most of them will be more expensive than just the standard alloys. They're easy to cast and have become the industry default. Therefore, we saw that before with the mechanical properties. If I need high strength, then I would definitely want to look into the 200 series alloys. That's the aluminum copper alloy family. It's the strongest of all aluminum casting alloys. They exhibit excellent high temperature strength. I mentioned before, copper is very resistant to high temperatures up to 250 degrees Celsius. After that, they get softer and we need to work with other elements, but that's already pretty high in terms of temperature for normal casting applications. Lack of significant intermetallic content leaves them pretty ductile, even when tempered to high strength. We have seen that with the A206 as an example. They should be considered when strength and fracture toughness levels are unobtainable with more user-friendly alloys. The castings are compatible with sand casting production because sand is a lot more forgiving than steel molds, or the part geometry is pretty simple. Then you can use a permanent mold as well. And better than find a foundry that is experienced in permanent mold casting of hot short alloys like this. Now, we saw before the 500 series. They can be very interesting, of course. That's the aluminum magnesium alloy family. They give us, as we have seen with the 535, very nice strength and ductility in the F-temper, so as cast, which can be a big cost saving, as you do not have to go through heat treatment, and especially if you are worried about distortion during heat treatment, that can help a lot and save money. They exhibit excellent corrosion resistance. That's why they are very often used for castings in marine applications. They machine or polish to a very high shine, excellent surface appearance. They can be anodized easily compared to especially the 300 series alloys, but most other alloys. They should be considered when corrosion resistance is a concern. So as I said, marine applications and surface appearance is critical in outdoor exposure. The castings need to be compatible with sand casting production or the part geometry simple enough for permanent mold or die casting. Now let's have a look at the 700 series alloys. That's the aluminum zinc magnesium alloy family. They exhibit moderate to high strength as naturally aged or artificially aged, so in T5 tempered. They can be brazed. That's pretty much the only alloy that can be brazed without a problem as a casting alloy. There's no thermal growth, so they have high dimensional stability over a large range of temperatures. And they should be considered for especially large casting requiring high strength to thick to heat treat. So they are naturally aged. They do not need to be heat treated, although you can heat treat them to interesting property package as well. Again, the parts can be brazed and anodized. That's the other family that is easily possible to anodize, and especially if tolerances are critical. For example, molds for blow molding plastic. If heat treatment must be avoided, and corrosion is not an issue, because particularly stress corrosion. But because of the zinc, we just learned that magnesium alloys are very corrosion resistant, but if you have aluminum zinc magnesium alloys, corrosion can be an issue. Again, the castings should ideally be compatible with sand casting production, or the geometry should be simple enough for permanent mold or die castings. So if you have to write an alloy purchasing specification, first of all, you want to specify your casting target chemistry. And I'm saying casting target chemistry. So that can be different from your ingot chemistry. And you need to measure the loss of all the volatile elements on the way. So especially magnesium and strontium, things like that, that you will lose when you're melting the castings, when you're melting the ingots, and when you're adding scrap parts or internal returns. You have to calculate, what am I losing in terms of volatile elements? And then you want to pick up the impurities. For example, iron. If you bring your metal in contact with iron or steel, whether it's anything that you're using for metal handling or of course your steel dies, you will have a certain iron pickup. You got to measure that and take it into account. And then define which elements you would rather want to add yourself in the foundry. For example, would you like to add strontium yourself because it's so volatile that it burns up so quickly, and you have always different times that the metal is sitting in the furnace, and then sometimes you have more or sometimes less burning off, so you prefer adding yourself, or you just tell your ingot supplier to come in with a higher level, that you're always on the safe side. And define a metal purchasing specification now, taking all of this into account. So let's have a look at an example. Take this target chemistry in the final casting. And those of you familiar with the castings obviously see I'm talking about an A356 here. It's 6.5 to 7.5% silicon, and let's say our target is 7%, and we have a limit on iron, copper, and manganese here. We have magnesium, a range, and a target, and so on. So you have to look at internal returns. And for that, I have just chosen this chemistry, for example. So we can see that I actually picked up a little bit of iron here. My usual 0.13 in the melting furnace has become a 0.14 with the returns. And I lost some magnesium and strontium, and that's a little less than I had before in my metal. Now let's say your internal returns represent, for example, 30% of the mix. So therefore your purchasing specification should be adjusted to our target. We have it here, and then the 30% returns and the 70% ingots now need to compensate for these changes in the chemistry in my returns so that together they will get me exactly to my target. We can see that here. And for silicon, we know there's no pickup or burn off. It's very stable. Iron, we see a small pickup, so we need a minor adjustment in the ingots. So my purity in my ingots, I want it to be higher than my target purity in my melting furnace. The magnesium burns off, so we need some adjustment in the ingots unless we want to add directly in the foundry and adjust the chemistry. Then the same thing with strontium. It burns off very similarly to magnesium, so it needs adjustment either in the ingot or as addition in the foundry. In this case, we chose to just put it in our ingot spec so we don't have to worry about it, and to be safe, we just put it at the maximum of the specification. Now, copper, manganese, chrome, nickel, and zinc are not picked up in our foundry typically, and they seem typically low in the ingots that we get, and so the usual maximum is sufficient in our case. If this is usually not the case and it's very important for us that the target is lower, then we might as well say, okay, to our ingot supplier, hey, we really want the copper to be below 0.01%. Other impurities, whatever we do not specify, is usually specified under the others and each other. So usually each other, for example, can be 0.05% and others total would be 0.15%. If we want certain elements to be lower than this, then we need to specify each of those elements individually. Now, which ones would we potentially have to specify individually? So those are the harmful impurities in the aluminum silicon based foundry alloys. So we know iron, of course, because it forms the iron needles that lower ductility severely, and we know that manganese can correct them, so we might just then say, okay, we want half of the iron content added as manganese content. So in this case, we might actually not say that we want exactly this manganese content. We can just say, well, we want half of the iron content of this alloy added as manganese. Calcium, for example, is a weak aluminum silicon eutectic modifier. It comes mainly from silicon addition, and it increases hydrogen solubility and reduces surface tension, and therefore it makes actually the hydrogen bubbles even bigger, and it leads to increased porosity. So if we know this is a problem for us, maybe we want to specify a certain ppm level in our incoming metal. Lithium, especially if we are, for example, low pressure furnace, low pressure caster, it encourages buildup of deposits in aluminum transfer system and dip tubes plugging in upstocks like in low pressure furnaces or in pumps. So if we know this is a problem, we might want to limit this to a certain very small ppm level. Phosphorus, if we know this is a problem, if we know that, well, we specified we want to have everything made with 100% recycled metal and it's made from scrap that potentially can contain phosphorus. We know phosphorus counteracts sodium and strontium modification, and modification failures means we want to specify phosphorus has to be below a certain ppm level. Antimony, it's another modifier for silicon eutectic, used in a lot of French wheels, also in some Japanese alloys. It reacts with either sodium and strontium to form cores into metallics with very adverse effects on castability and eutectic structure, so it's also a modification poisoner, and it can be found in some recycled wheels from French vehicles, for example. So if you know that this could be an issue, you might want to specify a very low ppm limit for this. The chemical analysis for this can sometimes be difficult as its spectrum actually overlaps that of iron. It's also classified as a heavy metal, so it's potentially toxic, and therefore you might just want to limit it in any case. Beryllium, usually used in very small portions, often 5 to 20 ppm in high magnesium alloys to reduce oxidation losses. Some people are concerned about potential berylosis risk if exposed to beryllium fumes or dust. Therefore, some people will put a specific limit, very low ppms for beryllium. What to do if you can't recycle internally. Sometimes castings can be very large and very difficult to remelt at the foundry, or the customer specification might simply not allow it. We have seen that before. Sometimes I see on a casting specification to be made with ingots only. So check with your ingot supplier for a scrap take-back solution, and if the scrap is not ideal to transport because it's just too much air and very little metal, and your ingot supplier is maybe even too far away, then consider shredding before shipping, or maybe remelting internally into something else, into another application, for example. If it can't be recycled into your ingots, then maybe into other high-value alloy ingots. And usually everything is better than recycling it back into A380, because A380 is kind of, some people don't like when I say that, but I just say it's the garbage alloy. If we can't recycle it in anything else that's of higher value, everything can go back into A380. Now let's have a quick look at defining testing and quality assurance for alloy and ingots. Analysis of the chemistry with a spectrometer is usually a must. I know some A380 diecasters do not do that because they just assume the alloy chemistry is okay and the customer doesn't really care much about properties, but for most castings it is important, and therefore you need to have a spectrometer. You need to check. The ingot producer needs to give you a certificate of analysis, and you want to counter check and then adjust if necessary at the casting plant. Then inclusion testing, and that can be done at the ingot producer already, especially if recycling content is allowed or even required. And at the casting plant, of course, and there it's really useful. So you might want to do the occasional PODFA at least once when you set up the process, and then regular checks, for example, with a K-mold or so. You do want to do hydrogen measurement at the casting plant. This is very useful, not so much at the ingot producer, because hydrogen is something you pick up when you're melting, when you're transferring the melt. Let's have a quick look at cost drivers in aluminum foundry alloys. Of course, first of all, that's the alloying elements. So first of all, know what they are doing in your casting and define the right level for each element, also considering their price, of course. Sometimes consider alternative elements that do the same at a lower cost. Define suitable ranges. The smaller your range, the higher the price for the ingots. But the larger the range, the greater might be the variation in properties. So you have to find the right compromise for your specific casting application. And then impurities. You have to define which elements are an impurity and therefore need a maximum, and then determine which elements require a maximum below the others each. And mind that the lower the maximums, usually the higher might be the alloy price. So better talk to your ingot producer to find out where you can easily make a compromise, where it doesn't hurt, where it doesn't increase the price, and what levels are acceptable. Then it's recycling content. So the higher the possible recycling content is, usually the lower the cost of making the alloy, because mind that recycled aluminum itself is cheaper, but it also comes already with alloy ingredients. Primary aluminum does not come with any alloy ingredients. I have to add everything and pay for it. Mind that recycling content also lowers the carbon footprint of your metal, and that might please you and also your customer. With that, we come to the conclusions. As you've seen, alloy selection is driven by the specific casting requirements and the casting process that you have chosen or that you have in-house. Certain casting processes require certain alloys and exclude others. Certain alloys can only be cast in a specific process. They would not give good results in others. Aluminum foundry alloys can really be tailored to many different requirements, many different properties through the right composition and casting process. The solidification rate and heat treatment also play a huge role in the final properties of the castings. As an OEM, please specify what you really want. So specify properties, tolerances, anything, but not what you think will give you what you want in a casting. Specify what you really want. And as the foundry, know your process and specify the alloy so it fulfills your requirements in the casting, taking into account that you pick up certain elements like iron, you lose others like magnesium, and account for mixing with internal returns, with scrap, etc. Do not specify simply a brand name alloy or that the alloy needs to be made from only primary aluminum. If that is what is needed, your ingot producer will do it. And otherwise, you will just pay a way too high of a price. Find out what the cost drivers are for your selected alloy and discuss it with your ingot supplier. Discuss which maximums and which ranges make sense for everybody, for you to achieve the right properties and for the ingot producer to use the cheapest input materials possible and give you the best price for it and get the highest possible recycling content and therefore lowest alloying costs. Maximize recycling content in your alloy. It will minimize costs and carbon footprint as well. If you can't recycle your scrap internally as it is, consider shredding and talk with your ingot supplier about a scrap take-back solution. With this, we're coming to the end of this webinar. Thank you very much. And if you have any questions, as I said in the beginning, here's my email address. I've also added Jay Armstrong's email. I'm sure you have that already, but just in case, we would like to hear from you. Get in touch with us, and I wish you a nice rest of the day or evening whenever you're watching this webinar. Goodbye.